In 2013, scientists set out to do something extraordinary. They attempted to recreate the entire evolution of the universe, from just after the Big Bang all the way to the present day. The simulation demanded an immense computational effort, consuming 19 million CPU hours, and it began with carefully predicted amounts of matter, dark matter, and dark energy believed to exist in those earliest moments after the universe was born. From there, the simulation was allowed to unfold on its own. The goal was simple but profound. If these initial conditions were correct, could they naturally evolve into the vast cosmic web of galaxies we observe today? What you are seeing represents only a tiny portion of that model. A cube spanning 32 million light-years across, where the expansion of the universe is visualized through variations in gas density and temperature alone. This is the intergalactic medium, even in what we call empty space. There are still a few particles drifting within every cubic centimeter. In this view, blue regions mark the coldest areas, while white regions reveal the hottest. Over millions of years, gravity begins to pull these sparse particles together, guided not only by their own mass, but by the invisible scaffolding of dark matter. Gradually, the gas condenses, forming structures that will one day become galaxies. And as it does, the temperature rises dramatically. At first glance, it looks like explosions are erupting from the densest regions. But galaxies are not actually exploding. What you are witnessing is something far more subtle and far more powerful. This is the heating of intergalactic gas. And each second in this visualization represents several million years of real cosmic time unfolding. At the heart of these intense regions lie quasars, the most luminous objects in the universe. These are not ordinary black holes, but black holes in an extremely active phase, capable of emitting more electromagnetic radiation than entire galaxies combined. When a quasar ignites, it releases an enormous surge of energy, blasting radiation outward, ionizing the surrounding gas, and heating it to extreme temperatures as it expands into space. This process is known as quasar mode, or active galactic nuclei feedback. It is not a permanent state. Black holes do not remain quasars forever. A quasar exists only when vast amounts of matter are falling inward, feeding the black hole and lighting up the region around it. As long as that fuel continues to flow, the quasar remains active, ejecting tremendous amounts of energy and material back into the cosmos. And this raises a question that seems almost paradoxical. How can something defined by its ability to consume everything around it also be one of the brightest sources of light in the universe? The answer lies not within the black hole itself, but in what surrounds it, the accretion disk. A swirling structure of matter spiraling inward becomes an arena of extreme physics. As material is torn apart and forced into orbit, friction and gravitational forces heat it to incredible temperatures, causing it to glow with extraordinary intensity, outshining entire galaxies in the process. These supermassive black holes often contain billions of times the mass of our Sun. The gravity surrounding them is almost unimaginable, as matter spirals through the accretion disk, orbiting faster and faster before falling inward. The friction between particles generates an enormous release of energy. The result is so extreme that a quasar can shine thousands of times brighter than our own Milky Way galaxy. In many cases, the quasar becomes so luminous that its entire host galaxy fades into obscurity beside it. Only with advanced instruments like the Hubble Space Telescope have astronomers managed to glimpse a few of these hidden galaxies behind the overwhelming glare. One of the most dramatic ways a quasar can ignite is during the collision of galaxies. When vast amounts of gas and dust are suddenly funneled into the central black hole, triggering an intense burst of activity. But this does not always happen. Not every galaxy collision produces a quasar. And not every black hole is constantly active. From the poles of these quasars, something even more extraordinary emerges. Narrow, powerful jets of energy shoot outward, extending far beyond the boundaries of the host galaxy itself. These jets can illuminate surrounding galaxies and vast clouds of cosmic dust like a beam cutting through darkness. When one of these jets happens to align directly with Earth, we observe the object as a blazar, an even more intense and focused source of radiation. These jets are believed to be driven by the black hole's magnetic fields, accelerating plasma to velocities approaching the speed of light and carrying enormous amounts of energy deep into intergalactic space. Yet, the era of quasars and blazars appears to be largely behind us. The nearest known quasar lies about 600 million light-years away, meaning the light we see today began its journey 600 million years in the past. What we are observing is a relic of a much more active universe. And yet, in the simulation, the bursts of energy do not fade with time. They continue, persistent and widespread. These later outbursts come from another member of the active galactic nuclei family, known as radio galaxies. Unlike quasars and blazars, which shine brightly across nearly the entire electromagnetic spectrum, radio galaxies are most prominent at radio wavelengths. The same underlying engine is at work, but the way energy is emitted has shifted. These ongoing eruptions are referred to as radio mode feedback, a quieter but still powerful mechanism shaping the structure of the universe even in its later stages. Eventually, the simulation reaches the present day, but as impressive as it is, it remains an approximation. It was able to track only around 1 trillion particles, a tiny fraction compared to the true number that exists in even a small region of space. Our understanding of the universe's fundamental parameters is still incomplete, and this leads to discrepancies, such as predicting more star formation than we actually observe. There are already plans to run more advanced simulations in the future, using improved data and deeper understanding, because by recreating the universe in this way, we are not just watching a model unfold. We are testing our entire understanding of how everything began, how structure formed, and how the cosmos evolved into what we see today. So, can galaxies explode? Not in the way we typically imagine, but if we define an explosion as the sudden release of immense energy in the form of radiation, then the answer is yes. On the largest scales imaginable, the universe is filled with events that, in every meaningful sense, are explosions written across the fabric of space itself. In October 2022, a flash of light tore through the cosmos. It was brighter and more intense than anything humanity had ever recorded. This is not an exaggeration. The burst was so powerful that it temporarily blinded gamma-ray detectors across the entire planet, releasing more energy in just a few seconds than our sun will emit over its entire 9 billion-year lifetime. Over the 18 months that followed, this event became the most intensely studied gamma-ray burst in history. Scientists gave it a name that reflected its sheer extremity: the brightest of all time. But as researchers began to analyze the data, each answer seemed to open the door to new and deeper questions. Gamma-ray bursts have been studied for decades, yet this one stood apart. It was closer than expected, far brighter than predicted, and strangely missing some of the signatures that should have accompanied an event of this scale. It forced scientists to question parts of the standard model, to consider new possibilities involving dark matter, and even to rethink how the universe forges heavy elements like gold. To understand why this event was so unusual, we first need to understand what gamma-ray bursts actually are. They are brief but extraordinarily intense flashes of high-energy radiation, lasting anywhere from a few milliseconds to several minutes. The first was discovered in 1967. Not by astronomers, but by military satellites searching for evidence of nuclear tests. Instead, they detected something far more distant and far more powerful. Since then, gamma-ray bursts have become one of the most valuable tools in modern astrophysics. They allow scientists to observe extreme physical conditions that cannot be recreated on Earth, offering a window into how stars are born, evolve, and ultimately die across the vast history of the universe. There are two primary types of gamma-ray bursts. Short bursts last less than 2 seconds and are typically caused by the collision of two neutron stars, or the merger of a neutron star with a black hole. These events are often followed by what is known as a kilonova, a brilliant emission of light produced as unstable elements rapidly decay, creating even heavier elements in the process. Long gamma-ray bursts, those lasting more than 2 seconds, are believed to originate from the catastrophic deaths of massive stars. When such a star collapses, its core can form either a neutron star or a black hole, triggering a powerful explosion known as a supernova. These events often occur in distant regions of the universe, where early generations of stars formed with very low amounts of heavy elements. When we observe them, we are looking billions of years back in time. In both cases, the newly formed black hole drives jets of particles outward in opposite directions, accelerating them to velocities approaching the speed of light. As these jets interact with surrounding material, they produce the gamma radiation that we detect across vast cosmic distances. So what made this particular event so extraordinary? It began with its duration. The burst lasted a full 10 minutes, and its afterglow remained detectable for 10 hours. It occurred in the constellation Sagitta, at a distance of roughly 2 billion light-years, making it significantly closer than most gamma-ray bursts ever observed. And that proximity changed everything, because, for the first time, we were not just observing an event at the edge of the universe. We were witnessing something powerful, relatively nearby, and unlike anything we had ever seen before. An explosion this bright, this close to Earth, is thought to occur only once every 10,000 years. The last time something like this happened, humanity had only just begun to farm the land. And while the evidence clearly points to a collapsing and exploding star as the source, this is where the story begins to unravel. Because a supernova alone is not enough to explain what was observed. This event was nearly 70 times more powerful than any gamma-ray burst ever recorded. At first, scientists believed it must have come from an extraordinarily massive star, something far beyond the norm. But when they examined the afterglow more closely, the data told a different story. The supernova behind it was not extreme at all. It was, in fact, surprisingly ordinary. To investigate further, astronomers turned one of the most powerful instruments ever built toward the event, the James Webb Space Telescope. Using its near-infrared spectrograph, revealed something unexpected. The explosion that produced this unprecedented burst of energy did not match its intensity. It was not nearly bright enough to justify what had been detected. So, what could have caused such an overwhelming flash? One possibility lies not in the total energy released, but in how that energy was directed. Imagine a flashlight glowing softly in the dark, spreading its light over a wide area. Now imagine taking that same light and compressing it into a narrow beam. Like a laser, the total energy has not changed, but its intensity in a specific direction becomes dramatically greater. If Earth happened to lie directly in the path of such a focused beam, the signal we detect would appear far brighter than the true energy output might suggest. This same principle can be applied to gamma-ray bursts. If a massive star collapses while spinning extremely rapidly, The jets it produces can become tightly collimated, narrower and more focused than usual, making them appear far more intense to an observer positioned along their path. In this case, the jets observed were among the narrowest ever recorded. But that was not the only anomaly. Scientists also detected far more high-energy particles than expected, moving at incredible speeds. After traveling for 2 billion years across the universe, these particles reached Earth with enough intensity to leave a measurable imprint on our planet itself. High above the surface, between roughly 50 and 1,000 kilometers in altitude, lies the ionosphere, a region filled with electrically charged particles. When the burst arrived, it disturbed this layer in a way comparable to a powerful solar flare, pushing it downward to lower altitudes. If radiation from an explosion 2 billion light-years away can alter the structure of our atmosphere, even for a brief moment, it raises a chilling question. What would happen if an event like this occurred much closer to home? The Large High-Altitude Air Shower Observatory in Daocheng, China recorded something unprecedented. Over the course of the initial burst and the fading afterglow, it detected tens of thousands of high-energy photons. This was not just unusual. It was far beyond anything ever observed in gamma-ray astronomy. So extreme that some astrophysicists believe it may be pointing towards something missing in our current models of physics. According to what we understand today, photons with such extreme energies should not be able to travel across 2 billion light-years of space and arrive intact. Along the way, they are expected to lose energy or be absorbed through interactions with the cosmic microwave background, collisions with intergalactic dust, and the stretching of their wavelengths due to the expansion of the universe. And yet, somehow, these photons made the journey. One proposed explanation is both elegant and deeply unsettling. It suggests that photons may not have traveled the entire distance as photons at all. Instead, they could have transformed into a hypothetical particle known as an axion, passed through space in this altered state, and then converted back into gamma rays upon encountering the magnetic field of our galaxy. Axions are theorized to be incredibly light particles and are considered one of the leading candidates for dark matter. But their existence remains purely hypothetical. There is no direct evidence for them. And if they do exist, they would lie outside the current standard model of particle physics. If this explanation is correct, then what we observed was not just an extreme astrophysical event, but a possible glimpse into entirely new physics. So far, the evidence suggests that this event began with the collapse of a massive star, forming a black hole in what is known as a collapsar. But collapsars are not only capable of producing long gamma-ray bursts, they may also be responsible for creating some of the most valuable elements in the universe: gold. At first, the connection seems unlikely. What could a distant gamma-ray burst possibly have to do with the gold found on Earth? To answer that, we need to step back and understand how elements are formed in the first place. Inside the core of a star, conditions are extreme beyond imagination. Pressures can reach around 200 billion times greater than the atmospheric pressure at Earth's surface. Under these conditions, nuclear fusion forces lighter elements to combine into heavier ones. For example, helium is formed when hydrogen nuclei fuse together. Through this process, stars are able to create elements from helium up to iron, a sequence known as stellar nucleosynthesis. But this process has a limit. Once iron is formed, fusion no longer releases energy. Instead, it requires energy to continue, making it an inefficient path for building heavier elements. So the question becomes unavoidable. Where do the rest of the elements come from? Where does gold come from? Currently, scientists believe there are at least two major pathways. One of them was recently confirmed through observations with the James Webb Space Telescope. When two neutron stars collide, they release an enormous flood of neutrons into the surrounding space. Nearby atomic nuclei capture these neutrons, becoming unstable, and then rapidly decay into new, heavier elements. This process is known as rapid neutron capture, or the R process. The scale of these events is staggering. A single neutron star collision may produce heavy elements equivalent to several times the mass of the Earth. But even this is not enough to explain everything. These collisions are rare and often take billions of years to occur. Yet when we observe some of the oldest stars in the universe, we find that heavy elements were already present long before such events could have happened frequently, which means there must be another source. And this brings us back to the event itself. There is a growing idea that collapses, like the one behind this extraordinary burst, could also serve as factories for heavy elements. In the final moments of their lives, massive stars are surrounded by layers of violently expanding gas, setting the stage for one of the most extreme environments in the universe. These violent explosions leave behind swirling disks of matter around a newly formed black hole. As the black hole begins to consume the surrounding material, it cannot absorb everything at once. The excess is driven outward in a powerful wind rich in neutrons. Within this extreme environment, the same rapid neutron capture process takes place, forging heavy elements such as gold, silver, and platinum. At first, this seems like a promising explanation. But even when scientists account for these kinds of stellar explosions, the numbers still do not add up. There simply is not enough gold produced to match what we observe across the universe. And the mystery deepens. When researchers analyzed the spectrum of this event, they found no clear evidence of heavy elements at all, casting doubt on the idea that collapses like this are major sources of gold. One possible explanation lies not in the explosion itself, but in its environment. The host galaxy of this event appears to have an unusually low metallicity, meaning it contains very few heavy elements to begin with. If the raw ingredients were missing, then even the most extreme processes may not have been able to produce the elements we expected to find. But this raises a deeper question. How do we even know how much gold should exist in the universe? How do scientists estimate the abundance of elements on a cosmic scale? There are two primary methods. The first involves analyzing the light from stars. By studying the absorption lines in stellar spectra, astronomers can determine which elements are present in a star's outer layers and in what proportions. The second method comes from meteorites, ancient remnants of the early solar system. By examining their composition, scientists gain an independent measurement of elemental abundances, including volatile elements like hydrogen and helium that are difficult to measure in stars. Remarkably, these two methods tend to agree, suggesting that our understanding is on the right track. But physics is rarely that simple. There are always exceptions. One of the most famous is lithium. According to standard Big Bang nucleosynthesis, the early universe should have produced about 3 times more lithium-7 than we actually observe today. And when it comes to lithium-6, the discrepancy is even more dramatic, with observations showing about 1,000 times more than predicted. This unresolved mismatch is known as the lithium problem, and it remains one of the most persistent challenges to our current cosmological models. It serves as a reminder that even our most established theories may still be incomplete. So the absence of heavy elements in this event does not necessarily invalidate the idea that gamma-ray bursts or collapses contribute to their creation. In fact, observations of ancient stars strongly suggest that an early rapid neutron capture process enriched the universe with heavy elements long before many neutron star collisions could have occurred. What this event tells us is not that our theories are wrong, but that they are incomplete. There may be additional processes, still unknown, that play a crucial role in shaping the chemical makeup of the cosmos. And if that is true, then this discovery reaches far beyond a single gamma-ray burst. It challenges our understanding of how the universe builds its most fundamental components. Where do the atoms that make up everything around us truly come from? Why do they exist in the proportions we observe? How much of our current model reflects reality? And how much remains hidden behind gaps in our knowledge? And what role, if any, does dark matter play in this process? We do not yet have the answers, but this event stands as a powerful reminder that our understanding of the universe is still evolving, shaped continuously by new data and new discoveries. The warm hues of orange, red, and pink spreading across the sky feel familiar, almost ordinary. But what you are seeing is only the final moment of a journey that began long before human history. If you trace these photons backward, from the retina at the back of your eye, through the layers of Earth's atmosphere, across the vast distance of 150 million kilometers separating our planet from its star, and deeper still into the violent interior of that star, you begin to uncover their true origin. There, at the core of the sun, lies the source of the warmth on your skin and the colors that paint the sky. A nuclear engine that has been burning for 4.5 billion years. A sphere of searing plasma, born from the remnants of ancient stars, shaped by forces that have been unfolding over cosmic timescales far beyond human imagination. To understand this, we have to go back to a time before the sun existed, before the planets, before anything we recognize as our solar system. Around 4.6 billion years ago, in a quiet region of the Milky Way, a vast cloud of gas and dust drifted through space. This was a giant molecular cloud, immense in scale, stretching across hundreds of light years and containing enough material to form millions of stars. Within this cloud were the scattered remains of earlier generations of stars. These stars had lived and died, exhausting their nuclear fuel and ending their lives in supernova explosions. In doing so, they seeded the surrounding space with heavier elements: carbon, oxygen, nitrogen, iron, mixed among vast amounts of hydrogen and helium. This mixture created the raw material for new stars and planetary systems to emerge. But a cloud this large does not collapse on its own without a trigger. Scientists believe that a nearby supernova sent a shock wave through the region, compressing parts of the cloud and pushing them past a critical threshold. Regions of higher density began to form, and under their own gravity, they started to collapse. This marked the birth of what would become our solar system, a dense region within the cloud known as the solar nebula. As the collapse continued, the cloud did not form a single object. Instead, it fragmented into multiple dense clumps. This process is governed by what is known as Jeans instability, a balance between gravity pulling inward and pressure pushing outward. When a region becomes large and dense enough that gravity overcomes this pressure, it collapses. Different parts of the cloud reach this threshold at different times, forming multiple collapsing cores rather than one single structure. One of these cores would become our Sun. In its earliest stage, it existed as a protostellar core, a dense, contracting sphere surrounded by infalling gas and dust. Gravity continued to pull material inward, compressing the core and raising its temperature. With each passing moment, it grew denser, hotter, and more defined, moving closer to becoming a true star. Eventually, this core transitioned into a protostar. It began to emit light and heat, not from nuclear fusion, but from the energy released as it continued to contract under its own gravity. Yet at this stage, Something crucial was still missing. The core had not yet reached the extreme temperatures required to ignite nuclear fusion, the process that would transform it into a stable, shining star. As the protostar continues to gather mass, the pressure and temperature at its core rise dramatically. For millions of years, our Sun existed in this embryonic phase, slowly contracting and heating, until its core finally reached around 10 million degrees Celsius. At that moment, something irreversible began. Hydrogen nuclei started to fuse into helium, releasing energy, and with that ignition, the Sun was born. At the same time, another force began to shape the system. The cloud of gas and dust surrounding the young star was never perfectly still. Even the slightest initial motion becomes amplified as the cloud collapses. This is the law of conservation of angular momentum. As the material is pulled inward, it spins faster and faster, much like a figure skater drawing in their arms to accelerate their rotation. Near the equator, some of this material is moving fast enough to remain in orbit around the forming star. But above and below this region, the motion is too slow to resist gravity. That material falls inward, feeding the growing core. The result is a flattened structure, a rotating disk known as a protoplanetary disk. Within this disk, a complex and chaotic process begins. Matter collides, sticks together, breaks apart, and reforms. Over time, this cosmic debris field gives rise to planets, moons, asteroids, and comets. Some material spirals inward and is consumed by the Sun, while other fragments survive, becoming the building blocks of the solar system we see today. With nuclear fusion now underway, the Sun gained the ability to resist its own gravity. The energy released from fusion creates an outward pressure, balancing the inward pull of gravity. This delicate equilibrium, known as hydrostatic equilibrium, marks the beginning of a stable phase in the life of a star. The main sequence. In this state, the Sun is no longer collapsing. Instead, it exists in a continuous balance between two opposing forces: gravity pulling inward and radiation pushing outward. This balance defines not only the present state of the Sun, but every stage of its life, from its violent birth to its eventual death. To understand how this balance is maintained, we need to look deeper into the process that powers it all. Nuclear fusion. Inside the core of the Sun, conditions are extreme. Temperatures reach around 15 million degrees, and pressures exceed 250 billion times that of Earth's atmosphere. In this environment, atoms cannot remain intact. Electrons are stripped away, leaving behind a plasma of free protons and electrons. These protons, all carrying positive charge, naturally repel each other through the electromagnetic force, often referred to as the Coulomb force. It is the same force you feel when trying to push together the like poles of two magnets. Under normal conditions, this repulsion would prevent fusion from ever occurring, even in the Sun's core, where particles move at tremendous speeds. Most collisions still do not have enough energy to overcome this barrier. To fuse, protons must come incredibly close enough for the strong nuclear force to take over and bind them together. And reaching that distance is the central challenge that nuclear fusion must overcome. This barrier is so immense that, in the early 1920s, physicists using classical models of particle behavior concluded that nuclear fusion should not be possible under the conditions found in the Sun's core. The temperatures and pressures simply did not seem high enough. Something was missing from the picture, and the answer came from a new framework that would reshape our understanding of reality itself. Quantum mechanics. In the quantum view of the universe, particles do not behave only as solid objects. They also behave like waves. And within this strange dual nature lies one of the most important phenomena in all of physics: quantum tunneling. This effect allows particles to pass through energy barriers even when they do not possess enough energy to overcome them in the classical sense. Inside the sun's core, quantum tunneling gives a small fraction of protons the ability to effectively bypass the Coulomb barrier. Even though they lack the kinetic energy required to overcome the electrostatic repulsion directly, quantum mechanics allows them a probability of appearing on the other side of that barrier. To visualize this, imagine the Coulomb barrier as a steep energy hill between two protons. In classical physics, a particle must climb over this hill to reach the other side. But in quantum mechanics, there is another possibility. The proton's wave-like nature allows it to pass through the hill itself, emerging on the other side without ever going over the peak. Without this effect, fusion in stars like the Sun would require temperatures in the billions of degrees Celsius, thousands of times hotter than what actually exists in the core. But because of quantum tunneling, fusion becomes possible under the conditions we observe. It is this subtle, probabilistic process that allows stars to shine. Once a proton has tunneled through the barrier, it can approach another proton closely enough for the strong nuclear force to take over. This force is far more powerful than the Coulomb force, but it acts only over extremely small distances. On the scale of femtometers, where 1 femtometer is equal to 10 to the power of minus 15 meters, roughly the size of a single proton. At this range, the strong nuclear force binds the protons together, but this is only the beginning of a chain of reactions known as the proton-proton chain, the primary source of energy in the Sun. This process accounts for roughly 99% of the Sun's total energy output. It begins when two free protons fuse to form deuterium, a heavier isotope of hydrogen, releasing a positron and a neutrino. This step is rare, but essential, because it allows the fusion chain to proceed. Next, the deuterium nucleus rapidly fuses with another proton to form helium-3, releasing a high-energy photon in the form of a gamma ray. In the final stage, two helium-3 nuclei collide and fuse to form helium-4, releasing two protons and a significant amount of energy as radiation. Although the proton-proton chain dominates in stars like our Sun, there is another fusion pathway that becomes important in hotter and more massive stars. This is known as the carbon-nitrogen-oxygen cycle. In this process, carbon, nitrogen, and oxygen nuclei act as catalysts, enabling protons to fuse into helium more efficiently at higher temperatures. In the Sun, this cycle contributes only a small fraction of the total energy output. But regardless of the pathway, the source of the energy remains the same. It comes from a subtle difference in mass. According to Einstein's equation, energy equals mass multiplied by the speed of light squared. E equals mc squared. In fusion reactions, the mass of the resulting helium nucleus is slightly less than the combined mass of the original 4 protons. That missing mass is not lost. It is converted into energy. And it is this energy that powers the Sun and lights up the universe. That missing mass does not simply vanish. It is transformed into energy, radiating outward from the Sun in an endless potok of light and heat. Every second, the Sun converts about 4.3 million tons of its own mass into energy. In other words, the Sun is constantly losing mass. To put that into perspective, this is roughly equivalent to turning the mass of about 3 million cars into pure energy every single second. This is the energy that ultimately sustains everything we experience on Earth. But before any of it can reach us, before a single photon can touch the surface of our planet. It must first escape the vast interior of the Sun, a distance of about 700,000 kilometers filled with chaos, density, and relentless interaction. To understand this journey, imagine following a single photon from the moment it is created in a proton-proton reaction deep within the core, all the way to the Sun's surface. This is not a straight path. It is not even close. In fact, this journey can take thousands, sometimes even hundreds of thousands of years. The journey begins in the core, a region that spans roughly 25% of the Sun's radius but contains nearly half of its total mass. Here, the density is extraordinary, around 160 grams per cubic centimeter, more than 20 times denser than iron. If an everyday object were made of material this dense, it would feel impossibly heavy, compressed beyond anything we encounter in our daily experience. For a photon, this environment is almost impenetrable. It cannot travel far before being absorbed by a nearby particle. Moments later, it is re-emitted in a completely random direction, only to be absorbed again. This cycle repeats endlessly. It is like trying to move through a crowded room where every step leads to a collision, forcing you to change direction again and again. This constant absorption and re-emission turns the photon's path into what physicists call a random walk. Instead of moving outward in a straight line, it drifts unpredictably, sometimes even moving back toward the center before eventually making progress outward. This motion is similar to Brownian motion, where particles move erratically due to countless tiny collisions. There is no preferred direction, no guiding path. A photon might come close to escaping, only to be scattered back inward again by chance alone. As this process continues, something else happens. The photon gradually loses energy. What began as a high-energy gamma ray is transformed step by step into lower-energy radiation, becoming X-rays, and eventually visible light by the time it reaches the outer layers of the Sun. Studying this hidden interior is one of the greatest challenges in astrophysics. The Sun's core is completely concealed beneath its outer layers, making direct observation impossible. But scientists have found indirect ways to understand what lies beneath. One of the most powerful tools is helioseismology, the study of waves that ripple across the Sun's surface. Much like seismologists use earthquakes to probe the interior of Earth, scientists analyze these solar vibrations to infer the temperature, density, and structure of the layers deep inside the star. Another key messenger comes in the form of neutrinos, elusive subatomic particles produced during fusion in the core. Unlike photons, neutrinos barely interact with matter at all. They pass straight through the Sun, escaping in just 2 seconds, completely unaffected by the dense chaos that traps photons for thousands of years. For decades, detectors on Earth observed fewer neutrinos than theoretical models predicted, leading to what became known as the solar neutrino problem. It was a discrepancy that hinted, once again, that even our most refined models of the universe might still be missing something fundamental. The mystery of the missing neutrinos was eventually resolved when scientists discovered that neutrinos can change their identity, or flavor, as they travel through space. This transformation confirmed not only key ideas in particle physics, but also validated our understanding of the nuclear processes occurring deep within the Sun's core. From there, our photon continues its journey outward, entering the radiative zone. This region extends from the edge of the core to about 70% of the Sun's radius. As it moves through this layer, the conditions begin to change. Temperatures gradually fall from around 15 million degrees down to roughly 2 million degrees. And the density decreases as well. dropping from values comparable to gold deep within the zone to less than that of water near its outer boundary. Even here, energy is still transported primarily through radiation. Photons continue their chaotic movement, scattering from particle to particle, slowly carrying energy outward. As the plasma becomes less dense, the photon gains slightly more freedom, traveling a bit farther between each interaction. But the sun remains incredibly opaque. Even outside the core, just a few centimeters of solar material can block as much light as hundreds of meters of water. Our understanding of this hidden interior comes from models like the Standard Solar Model, a mathematical framework built on principles such as hydrostatic equilibrium, energy conservation, and radiative transfer. By applying the laws of physics tested here on Earth, scientists can simulate and reconstruct conditions in regions we can never directly observe. These models describe how energy moves through the sun, how photons interact with dense plasma, and how transparent the solar material becomes at different temperatures and densities. From this, we can determine where one layer ends and another begins, mapping the structure of the sun with remarkable precision. There is something powerful about this. Mathematics allows us to explore places we will never visit, to understand processes unfolding deep within a star, far beyond our reach. In a way, it mirrors the strange logic of quantum tunneling itself, where particles cross barriers that should be impossible to overcome. As the photon approaches the outer boundary of the radiative zone, it enters a thin transitional layer known as the tachocline. This region marks the boundary between the relatively stable radiative zone and the turbulent convective zone above it. The tachocline is a place of sharp contrast. Below it, the plasma moves in a more orderly way. Above it, the sun begins to churn and boil. These extreme differences are believed to play a crucial role in generating the sun's magnetic field. The twisting and shearing motions within this layer amplify magnetic forces, shaping sunspots and driving solar flares that ripple across the star's surface. Passing through this narrow boundary, the photon enters the convective zone. This region extends from about 70% of the sun's radius all the way up to the visible surface, known as the photosphere. Here, temperatures have dropped to below 2 million degrees Celsius, and the plasma is no longer dense enough to efficiently transport energy through radiation alone. Instead, the plasma becomes unstable and begins to move in vast convection currents. Much like water boiling in a pot, hot plasma rises toward the surface in enormous cells known as granules. Each of these structures can span thousands of kilometers, surging upward under buoyant forces at speeds of hundreds of meters per second. Like a ball forced beneath water, snapping back toward the surface with unstoppable momentum. The scale of this motion is almost beyond comprehension. The energy required to lift such immense volumes of matter against the sun's gravity is staggering. Even if you imagine the combined force of 10 billion hurricanes, you would only begin to approach the intensity of what is happening here. This convective motion becomes a far more efficient way to transport energy, generating vast rolling currents of plasma that churn and twist continuously. This marks a fundamental shift in how energy moves through the sun. In the deeper layers, photons slowly diffused outward through countless interactions. But here, energy is carried by motion itself. Hot plasma rises, cools as it approaches the surface, and then sinks back down, creating a dynamic cycle that transfers energy outward far more effectively than radiation alone. As the photon is carried upward within these currents, it eventually reaches the photosphere, the visible surface of the sun. By this point, the temperature has dropped to around 5,500 degrees Celsius, and the plasma has become thin enough to allow light to escape without being constantly reabsorbed. This layer is surprisingly shallow, only about 500 kilometers thick. Yet it is from here that all the sunlight we see is emitted. Above it lies the corona, an outer atmosphere of the sun that is incredibly diffuse, with a density roughly 1 billion times lower than the photosphere. For our photon, there is little left to impede its escape. And so, after a journey that may have taken hundreds of thousands of years, the photon finally breaks free. It leaves the surface at the speed of light, beginning a new journey across the vastness of space. The neutrino created alongside it, however, has long since departed, already far beyond the Milky Way. Having escaped the Sun in just 2 seconds, since entering its stable phase as a main sequence star, the Sun has not remained unchanged. Over billions of years, nuclear fusion has gradually altered the structure of its interior, increasing its brightness and slowly reshaping its future. As hydrogen continues to fuse into helium, the supply of hydrogen in the core is steadily depleted. In its place, helium accumulates as an inert ash. Unlike hydrogen, helium requires much higher temperatures to undergo fusion, so it does not immediately contribute to energy production. As this helium builds up, the core becomes denser. Helium nuclei are more massive than hydrogen nuclei, and their accumulation increases the overall density of the core. At the same time, because helium is not actively fusing, it does not generate the outward pressure needed to counteract gravity. As a result, gravity begins to take over. The core contracts further under its own weight. But this contraction is not the end. As the core compresses, its temperature rises. And because nuclear fusion is extremely sensitive to temperature, even a small increase leads to a significant increase in the rate of hydrogen fusion in the surrounding layers. This increase in fusion releases more energy, making the Sun gradually brighter and restoring the balance between gravity pulling inward and radiation pushing outward. Over its lifetime, the Sun's energy output has already increased by about 30%. And this trend will continue for billions of years as long as hydrogen fusion remains active in the core. Deeper inside, the radiative zone has also changed. As the core becomes hotter, it produces more energetic photons, which interact more frequently with the surrounding plasma. This makes the region more opaque, trapping photons for longer periods and slowing their outward journey. At the same time, the convective zone has expanded slightly, driven by the increasing energy flowing from the core. But this balance is not permanent. Over the next 5 billion years, the Sun will continue to burn through its hydrogen fuel. Eventually, the core will become dominated by helium, an inert residue that cannot sustain fusion under the existing conditions. When that moment arrives, the equilibrium will break. Gravity will once again take control, compressing the core further. As it contracts, the temperature will rise dramatically until it reaches a new threshold. Then, in a sudden and violent event known as the helium flash, helium will begin to fuse into heavier elements such as carbon and oxygen. At the same time, the outer layers of the Sun will expand enormously. The star will swell into a red giant, growing so large that it may engulf Mercury and Venus, and possibly even Earth. This transformation marks a new phase in the life of the Sun, one defined once again by the delicate struggle between gravitational collapse and the outward force of energy released from its core. As this process continues, the Sun will shed its outer layers, casting them into space to form a glowing, expanding shell known as a planetary nebula. What remains at the center will be the core, no longer capable of fusion, cooling slowly over time. This remnant will become a white dwarf, Earth-sized ember. the final stage of a star that once powered an entire solar system. And so, from its birth in a collapsing cloud of cosmic gas to its eventual transformation into a fading stellar remnant, the life of the Sun is a story of balance, in change, and inevitable evolution. Now, return for a moment to that quiet horizon, where sunlight spreads across the sky. The colors you see, the warmth you feel, are the final expression of a journey that began deep within a star. A journey that may have taken hundreds of thousands of years before reaching you. Each photon carries with it the history of its origin. Born in the crushing pressures of a stellar core, wandering through a sea of plasma, and finally escaping into the vastness of space to arrive at your eyes. It is easy to take this daily moment for granted. But behind every sunrise lies a chain of events stretching across billions of years. From the collapse of a massive cosmic cloud to the fusion reactions that continue to power the Sun today. And there is still so much we do not yet understand. Our closest star continues to hold secrets about its structure, its evolution, and its influence on the future of our solar system. Beneath its thick clouds, Venus tells a very different story. A world of relentless heat and crushing pressure. Its surface shaped by vast volcanic plains and violent geological forces. For centuries, its true nature remained hidden behind an impenetrable veil, until a mission in the late 20th century finally revealed what lay beneath. On May 4, 1989, the Space Shuttle Atlantis launched from the Kennedy Space Center, carrying with it a remarkable payload, a spacecraft destined for Venus, one that would become the first deep space probe ever deployed from a shuttle, and one that would soon transform our understanding of our nearest planetary neighbor. For 4 years, the Magellan spacecraft carried out an extraordinary mission. Studying Venus in unprecedented detail, it mapped about 98% of the planet's surface, achieving a resolution as fine as 100 meters. The images it returned fundamentally changed our understanding of this mysterious world. Earlier missions had only offered glimpses. In 1974, Mariner 10 captured images of Venus's thick cloud layers as it passed by on its way to Mercury. A year later, Soviet landers became the first and only spacecraft to touch down on the surface, sending back haunting images of a barren and hostile landscape. But those cameras could see only a few meters in any direction, and within hours, they were destroyed by the planet's crushing pressure and extreme heat. During the 1970s, the Pioneer Venus orbiter provided the first radar maps of the planet, but the resolution was low and the coverage incomplete. It was like trying to map the entire Earth while being unable to zoom in beyond 75 kilometers. Entire cities would disappear into a single pixel, making detailed understanding impossible. Even worse, large regions near the poles were missing entirely. Scientists knew they needed something far more advanced. They wanted to see everything: the landforms, the tectonic structures, the evidence of impacts, erosion, and even clues about what lay beneath the surface. To achieve this, they designed one of the most ambitious planetary missions ever attempted. That mission was Magellan. To accomplish its goals, the spacecraft relied on several key innovations. The first challenge was penetrating Venus's dense atmosphere. Magellan used a powerful synthetic aperture radar system built around a high-gain antenna measuring 3.7 meters across. By collecting multiple radar signals from different positions in orbit and combining them, the system effectively simulated a much larger antenna, revealing surface details with remarkable clarity. Second, the spacecraft followed a carefully planned polar orbit. As it circled Venus, it scanned the surface in long north-to-south strips. Each orbit lasted 3 hours and 15 minutes. And over the course of 6 mapping cycles, each lasting 243 days, the spacecraft gradually built a complete picture of the planet. The first 3 cycles focused on surface mapping, while the later cycles gathered data about the planet's gravitational field. By May 15, 1991, at the end of its first mapping cycle, Magellan had already exceeded expectations, covering over 83% of the surface. By the completion of the third cycle, it had mapped 98% of Venus at resolutions ranging from 100 to 250 meters. In total, the spacecraft transmitted about 150 gigabytes of data back to Earth, more than all previous planetary missions combined at the time. After completing its primary mapping objectives, the mission entered a new phase. By carefully tracking changes in the spacecraft's motion as it orbited Venus, scientists used the Doppler effect to measure variations in the planet's gravitational field. This revealed valuable insights into the internal structure and density distribution hidden beneath the surface. The results were extraordinary. The images returned were about 10 times sharper than any previous radar images, and roughly 250 times more detailed than those from earlier missions. For the first time, humanity could truly see what lay beneath Venus's thick, toxic clouds. Where earlier missions had shown only vague outlines, Magellan revealed a world in stunning detail. A landscape shaped by forces both familiar and utterly alien, offering our first real glimpse of the surface of our closest planetary neighbor. This global mosaic took nearly a decade to assemble. Built from vast amounts of radar data collected by Magellan. And when you begin to zoom in, the first thing that stands out is something unexpected. Venus has surprisingly few impact craters. Compared to worlds like the Moon or Mars, its surface appears almost untouched. Magellan identified only around 940 impact craters across the entire planet. Many smaller impacts never made it to the surface at all. They're meteors burning up in the dense atmosphere long before impact. But even the craters that do exist behave differently. When an impact occurs on Venus, material is blasted outward, forming strange, blanket-like patterns around the crater. These ejecta deposits leave behind distinctive shapes that allow scientists to estimate the angle of impact, the energy released, and even the composition of the surface beneath. What makes them truly unusual is their appearance. Instead of the dry, ballistic patterns seen on airless worlds, these ejecta flows often resemble molten lava, spreading outward in smooth, flower-like shapes. The reason lies in the extreme conditions at the surface. The high temperatures allow this material to remain partially molten for far longer than expected. A striking example can be seen in Adlevar crater. On the Moon, debris from an impact follows a simple arc through space before landing. But on Venus, the thick atmosphere interacts with the ejected material, creating powerful winds that push it outward along the surface. The result is a set of unusual streaks, including distinctive horseshoe-shaped patterns found nowhere else in the solar system. Another dramatic case is Adam's crater, which spans about 90 kilometers in diameter and features an outflow tail stretching nearly 600 kilometers. This extended flow is likely composed of molten rock, kept fluid for long periods by the intense heat and pressure at the surface. The scarcity of craters suggests something profound. Venus's surface is not ancient and static. It is relatively young. Data from the mission supports the idea that the planet underwent a global resurfacing event between 300 million and 500 million years ago. What could have caused such a massive transformation? The answer appears to be volcanism on a planetary scale. Before this mission, scientists already suspected that Venus had volcanic features. But what they discovered was far more extreme. Around 85% of the planet's surface is covered in volcanic flows. Vast plains of solidified lava stretch across the landscape. forming structures unlike anything seen on Earth. Among these are enormous pancake domes, some reaching about 65 kilometers across, yet rising less than 1 kilometer in height. These features likely formed from highly viscous lava that spread outwards slowly before cooling and collapsing, leaving behind cracks and pits across their surfaces. Elsewhere, immense lava flows extend for hundreds of kilometers, covering fractured plains beneath massive shield volcanoes such as Sapas Mons and Maat Mons. By studying the shapes and patterns of these formations, scientists can distinguish between different types of volcanic activity, from localized eruptions to vast regional flooding events. Maat Mons itself rises to about 8,000 meters in height, making it comparable to the tallest mountains on Earth. It is a classic shield volcano, with broad, gently sloping sides formed by flowing lava, similar in structure to volcanoes found in Hawaii. But not all volcanic features on Venus are so large. Smaller domes are scattered across the surface, formed by thick lava that does not travel far before piling up around its source. In some regions, these domes appear between different types of lava flows, suggesting multiple phases of volcanic activity overlapping across time. All of this evidence points to one conclusion: volcanism has been the dominant force shaping Venus, and it may not be finished yet. In 2024, researchers revisiting archived mission data discovered signs that at least 2 volcanoes may have erupted during the spacecraft's mission in the early 1990s. This supports earlier findings suggesting that Maat Mons itself may have been active as recently as 1991. So beneath this seemingly static surface, something may still be moving. And to understand what is happening below, we have to look at one of the most intriguing features on Venus: the corona. Consider a structure like Yavin corona, stretching roughly 500 kilometers across the surface of Venus. Features like this offer a rare glimpse into the forces shaping the planet from below. When hot magma rises from deep within the mantle and pushes upward against the lithosphere, it deforms the surface in dramatic ways. On Earth, this kind of activity is moderated by plate tectonics. The crust is divided into moving plates that drift over mantle plumes, forming volcanic chains such as the Hawaiian Islands. But Venus is different. It appears to have a single, continuous crust, with no evidence of moving plates. As a result, when mantle plumes rise, they push the surface upward until it bulges and stretches. Eventually, as the magma cools and the pressure subsides, the surface collapses inward. The result is a corona, a vast circular structure marked by fractures, ridges, and complex patterns that record the rise and fall of molten material beneath. Despite being hundreds of millions of years old, many of these features remain remarkably well preserved. There are around 500 coronae scattered across the planet, distributed in patterns that do not align with plate boundaries, reinforcing the idea that Venus lacks the kind of plate tectonics seen on Earth. Instead, its lithosphere appears too thick or too strong to break apart into mobile plates. All of this points to a very different style of planetary behavior. Rather than moving plates recycling the surface over time, Venus seems to operate under what is known as a stagnant lid regime. The crust remains largely fixed in place, while forces from below push, stretch, and deform it. This difference may be central to understanding Venus's extreme climate. On Earth, plate tectonics plays a crucial role in regulating atmospheric carbon. Rainwater interacts with rocks, forming minerals that eventually wash into the oceans. Over time, this carbon is locked away in sediments and carried deep into the planet through subduction, helping to stabilize the climate. On Venus, this cycle does not exist. With no active plate tectonics, carbon dioxide is not efficiently removed from the atmosphere. Instead, Heat builds up beneath the surface, and greenhouse gases accumulate. As internal pressure increases, the system becomes unstable, eventually leading to catastrophic resurfacing events that release vast amounts of energy and reset the planet's surface. Then the cycle begins again. The exact timing of the last global resurfacing event is still uncertain, but estimates suggest it occurred around 300 million years ago. Another clue to Venus's complex interior lies in structures known as tesserae, found primarily in the planet's highland regions. These are some of the most deformed terrains on Venus. With a distinctive tile-like pattern of ridges and valleys, they cover about 8% of the planet's surface and are believed to be among its oldest visible features, dating back roughly 750 million years. First identified by earlier missions, these regions were revealed in extraordinary detail by Magellan. One of the most striking examples is Alpha Regio, a vast highland area showing intense deformation. Yet even now, scientists are not entirely sure how tesserae form. They may be composed of volcanic material that has been heavily deformed, or they could represent fragments of an ancient continental crust, shaped by immense compressional or extensional forces. If so, they may hold vital clues to Venus's distant past, possibly even preserving evidence of what the planet's climate was like billions of years ago. Perhaps most remarkable of all, the mission may have captured evidence of ongoing geological activity. In a region known as Aphrodite Terra, an area roughly the size of Africa, two images taken months apart revealed a subtle but significant change. A bright, flow-like feature appeared where none had been before. The most likely explanation is a massive landslide, possibly triggered by a Venus quake, suggesting that even today, beneath its seemingly static surface, Venus may still be a geologically active world. On October 13th, 1994, after completing one of the most successful deep space missions in history, the spacecraft made its final descent into the atmosphere of the very planet it had spent 4 years studying. As it plunged downward, it continued transmitting data from the upper layers of Venus, sending its final measurements back to Earth before being consumed by the planet's crushing heat and pressure. More than 30 years later, Magellan remains one of our most important sources of information about Venus. And like all great scientific missions, it answered some questions while raising many more. Did Venus ever have liquid water on its surface? If it did, could it once have supported life? How did this world evolve into the hostile environment we see today? And is it still geologically active beneath its thick clouds? Future missions are now being prepared to continue this exploration. Over the coming years, new spacecraft will return to Venus to study its atmosphere, its surface, and its internal structure in far greater detail. One mission will send a probe deep into the atmosphere, collecting data on its chemical composition and possible history of water as it descends toward the surface. Another will orbit the planet, searching for signs of active volcanism and tectonic activity, mapping heat flow and analyzing the composition of ancient terrains. Together, these missions aim to answer one of the most compelling questions in planetary science. Is Venus a glimpse of Earth's future? Or is it a fundamentally different world shaped by forces we do not yet fully understand? Now, shift your focus to another extreme world, much closer to the Sun. Mercury, the innermost planet of our solar system. At first glance, Mercury might seem simple, just a small rocky body orbiting close to the Sun. But in reality, it is far more complex and fascinating than it appears. Its surface may remind you of the Moon, covered in craters and ancient plains. But when you look more closely, it reveals a world with its own unique characteristics. Unlike the Moon's muted tones, Mercury displays subtle variations in color across its surface. And beneath that surface lies something even more intriguing. Mercury is composed of approximately 70% metallic material and 30% silicate rock, making it far more metal-rich than most other planets. This composition gives Mercury an unusually high density. It is the second densest planet in the solar system, with an average density of about 5.4 grams per cubic centimeter, only slightly less than Earth's density of about 5.5 grams per cubic centimeter. If Mercury were the same size as Earth, its surface gravity would be very similar. But because it is much smaller, its actual surface gravity is only about 3.7 meters per second squared. Despite its size, this value is surprisingly close to the gravity experienced on Mars. Even though Mars is significantly larger, this tells us something important. Mercury's interior must be extremely dense, dominated by a large metallic core. To put this into perspective, consider two of the largest moons in the solar system, Ganymede, orbiting Jupiter, and Titan, orbiting Saturn. Both of these moons are actually larger than Mercury in size. Yet despite their greater dimensions, they contain far less mass, highlighting just how dense and compact Mercury truly is. These two massive moons may be larger than Mercury in size, but they contain far less mass, revealing just how dense and compact Mercury truly is. If you examine Mercury's surface more closely, it begins to resemble our moon. It is covered in vast plains and heavily cratered terrain, suggesting that it has been geologically inactive for billions of years. But this was not always the case. One of the most striking features of Mercury's surface is the presence of long, narrow ridges that stretch for hundreds of kilometers. These structures likely formed as the planet cooled over time. As its core and mantle contracted, the already solid crust was forced to compress and buckle, creating these enormous wrinkles across the surface. Another defining feature is the Caloris Basin, one of the largest impact structures in the entire solar system. It spans roughly 1,550 kilometers in diameter. The impact that created it was so powerful that it triggered widespread volcanic activity and formed a ring of mountains rising more than 2 kilometers above the surrounding terrain. On the opposite side of the planet, directly across from this basin, lies a strange and chaotic region known as the Weird Terrain. Compared to the rest of Mercury, this area is fractured and uneven, likely shaped by shock waves that traveled through the planet from the original impact. Conditions on Mercury's surface are extreme. Temperatures vary dramatically depending on location. They can drop to around -73 degrees Celsius in some regions and rise to over 400 degrees Celsius in others. At the poles, temperatures never rise above roughly -93 degrees Celsius, because these regions remain in permanent shadow, shielded from direct sunlight. At the point directly facing the sun, temperatures can reach around 400 degrees Celsius, while on the night side, they fall to approximately -63 degrees Celsius. This enormous variation is due to Mercury's lack of a substantial atmosphere. Because Mercury is small and close to the Sun, its gravity is not strong enough to hold onto a thick atmosphere over long periods of time. Without an atmosphere to trap heat, the side facing the Sun becomes intensely hot, while the dark side loses heat rapidly and becomes extremely cold. However, Mercury is not completely without an atmosphere. It has what is known as an exosphere, an extremely thin layer of particles loosely bound to the planet. Unlike a true atmosphere, the density is so low that particles rarely collide with one another. Instead, atoms are constantly being lost to space and replenished by interactions such as impacts and solar radiation. When the solar wind strikes Mercury, it can strip atoms away from this exosphere, creating a faint tail of particles streaming behind the planet. Even Earth has an exosphere, though it begins much higher above the surface, at around 600 kilometers, marking the transition between atmosphere and space. Despite its harsh environment, Mercury still holds surprises. Observations have confirmed that some craters near its north pole contain water ice, preserved in permanently shadowed regions. It also possesses a global magnetic field, something Mars largely lacks. Although Mercury's magnetic field is only about 1.1% as strong as Earth's, it is still powerful enough to deflect a portion of the solar wind. One of the most fascinating aspects of Mercury is its motion through space. Its orbit is highly elongated, ranging from about 46 million kilometers to 70 million kilometers from the Sun. It completes a full orbit in approximately 88 Earth days. But its rotation is even more unusual. Mercury exhibits what is known as a 3-to-2 spin-orbit resonance. This means that for every 2 orbits around the Sun, it rotates 3 times on its axis. As a result, although a single rotation takes about 59 Earth days, a full solar day, from one sunrise to the next, lasts 2 Mercurian years. If you were standing on Mercury, the sky would behave in a way that feels almost impossible. The sun would rise, move across the sky, slow down, and then appear to reverse direction before continuing its path again. A full cycle of day and night would take an entire Mercurian year, meaning that both daylight and darkness each last for incredibly long periods of time. The Sun appears to move backward in Mercury's sky because of a remarkable alignment of motion. About 4 Earth days before Mercury reaches its closest point to the Sun, known as perihelion, the speed of its orbit matches the speed of its rotation. At that moment, the Sun seems to stop moving entirely, frozen in the sky. As Mercury continues along its orbit and reaches perihelion, its orbital speed briefly exceeds its rotational speed. To an observer standing on the surface, the Sun would appear to reverse direction, drifting backward before eventually resuming its normal path about 4 Earth days later. This strange motion becomes even clearer when viewed from above. Near the poles, the Sun can appear to pause, linger, and then continue its journey, creating a sky unlike anything experienced on Earth. Mercury's orbit has another important characteristic. It is tilted by about 7 degrees relative to the plane of Earth's orbit. Because of this inclination, Mercury only passes directly between Earth and the Sun under very specific conditions. These events, known as transits, occur roughly once every 7 Earth years. Its rotation is equally unusual. Mercury's axial tilt is almost 0, with a measured value of just 0.027 degrees. This is even smaller than Jupiter's tilt, which is about 3.1 degrees. As a result, Mercury experiences almost no seasonal variation. Its extreme temperatures are driven almost entirely by its proximity to the Sun and its slow rotation, rather than any tilt of its axis. And if you were to look back toward Earth from Mercury, you would see something almost surreal. Our entire planet, every ocean, every city, every living being, reduced to a tiny point of light, just a few pixels across against the vast darkness of space.